In the silent, unending ocean of space, a ghost has been traveling for a very, very long time, a mysterious visitor from a star system we've never seen. It may have journeyed for billions of years, a frozen relic carrying the chemical secrets of a universe that existed long before our own. And now it's wandered into our backyard. The James Webb Space Telescope has just analyzed this alien comet, and what it found is rewriting the story of our own cosmic origins. It began quietly, like all great discoveries often do. July 1st, 2025, an ordinary day on Earth, but somewhere high in the Chilean desert, under skies so dark that the Milky Way looked like spilled silver, an automated telescope caught a glimpse of something that would soon grip the imagination of the entire astronomical world. The telescope was part of the Atlas survey, a vigilant network designed to hunt for hazardous asteroids that might one day threaten our planet. Night after night, it scanned the heavens with mechanical precision, capturing faint dots of light, comparing them to previous frames, and flagging anything that moved. That night, the software flagged a faint speck of light creeping across the sky. It wasn't bright, it wasn't spectacular. To the untrained eye, it was just another pixel of light in an endless ocean of stars. But in science, greatness often hides in the subtle. The system gave it a dull, bureaucratic name, A11PL3Z, the kind of temporary designation astronomers use before a discovery proves itself worth remembering. For a few days, no one paid it much attention. The skies were full of noise, after all false positives, noise spikes, cosmic rays, and thousands of asteroids whose paths had already been mapped. But then came the follow-up observations. Teams in Hawaii, Arizona, and Spain began tracking its motion, each taking new data points, refining its orbit. What they saw made them stop. The math didn't make sense. The object wasn't just moving fast, it was moving too fast. At first, they thought it might be a data error, perhaps a calibration glitch, but the numbers held up. The mysterious object was cutting across the solar system at over 58 kilometers per second, faster than any normal asteroid, faster than any comet bound to the sun. It was moving on a hyperbolic trajectory, a path that no object born from our solar system could naturally follow. For those who study the cosmos, that word hyperbolic changes everything. It's a mathematical signature of something that doesn't belong. Every planet, every moon, every comet that formed alongside our sun billions of years ago follows an elliptical orbit. Ellipses are closed loops, meaning they come back again and again, bound forever by the sun's gravity. But a hyperbola is open a one-way path through the solar system. A hyperbolic orbit is the cosmic equivalent of a stranger passing through town, never to return. As data poured in from observatories across the world, the truth became undeniable. This object wasn't from around here. It wasn't orbiting the sun, it was visiting it. Astronomers had seen this kind of thing only twice before. The first was in 2017, when an oddly shaped object called Oumuamua had come screaming through the inner solar system, the first confirmed interstellar visitor. It was cigar-shaped, tumbled chaotically, and reflected light in strange ways. Some had even whispered about alien probes, though science later leaned toward a natural explanation. The second, in 2019, was 2I/Borisov, a comet more familiar in appearance, trailing a bright, icy tail, but carrying the chemical fingerprints of a world far from our own. And now, in 2025, the third had arrived, a faint, unassuming smudge that would soon be known as 3I/Atlas. The discovery announcement hit the astronomical community like a wave. In less than 24 hours, telescopes across the globe began reorienting. Everyone wanted a piece of this interstellar traveler. The 3I designation marked it as the third interstellar object ever confirmed. And the Atlas A portion paid homage to the survey that first found it, a quiet recognition of human vigilance, of machines that never sleep, of data that never lies. For astronomers, this was the cosmic equivalent of finding a message in a bottle, one that had drifted through the black ocean of interstellar space for untold ages, only to wash up briefly on our celestial shores. Every particle, every molecule of that comet was a relic from somewhere else, a frozen time capsule from a distant sun. For decades, scientists had dreamed of studying such an object up close, and now, for the third time in history, the universe had delivered one to our doorstep. Yet, even as the first measurements came in, 3I/Atlas was already challenging expectations. It wasn't bright like typical comets, nor was it behaving like an asteroid. Its light curve showed subtle fluctuations, hinting at rotation or an irregular shape. Early radar attempts struggled to get a clean echo. It was simply too faint and too fast. But astronomers didn't need to touch it to know that it was special. Its velocity alone told the story of a journey that defied comprehension. To put it in perspective, 58 kilometers per second means it could travel from New York to Tokyo in less than 2 minutes. But in space, speed isn't just about motion, it's about history. Every object carries within its trajectory a record of where it came from. By analyzing its motion relative to the sun and the background stars, astronomers could estimate the region of the galaxy it had originated from. It appeared to be coming from a direction in the constellation links, a relatively quiet region of the sky, not linked to any nearby stars. Whatever home it once had was long gone from its path. This was a true drifter, forged under an alien sun, now passing briefly through ours. As news spread, the story spilled beyond the walls of observatories and into the public imagination. An alien visitor returns, one headline read. Another messenger from the stars, said another. Social media exploded with speculation. Was it artificial? Was it carrying life? Had we just found evidence of another civilization's debris? Scientists were careful to temper expectations. It's not a spacecraft, one NASA official said with a chuckle during a press briefing, but it's no less exciting. This is a piece of another solar system, a true interstellar fossil. And that was the beauty of it. Every world, every asteroid, every comet in our solar system shares a common origin story, the dusty debris left behind from the birth of the sun. They are family, bound by the same chemistry and the same gravitational ties. But 3I/Atlas was a stranger, a visitor whose entire existence began under a different star, perhaps orbiting a different kind of sun, perhaps in a system with its own planets and its own story of creation and destruction. When the first color images of the comet were released, they looked deceptively ordinary, a fuzzy dot surrounded by a faint halo, not unlike the thousands of comets catalogued before it. But for scientists, that image represented something far greater. It was the face of the unknown. Light that had traveled across interstellar space for millions, maybe billions of years, had just reached our detectors. That faint glow was a whisper from another world. The naming process itself was symbolic. 3I for the third interstellar object, Atlas for the telescope that found it. Together, the name read like a statement, a third chapter in humanity's growing book of interstellar encounters. Oumuamua had shown us that interstellar travel wasn't just theoretical. Borisov had confirmed that comets too could make the leap between stars. And now Atlas was offering a chance to look deeper, not just to see another traveler, but to truly study one, to catch it early, while it was inbound, before it slipped away into the dark again. For astronomers, timing is everything. Oumuamua had been discovered too late. By the time we noticed it, it was already leaving, too fast and too faint to study properly. Borisov had been better a comet with a clear tail, observed for months. But 3I/Atlas was something different. It had been spotted early while it was still beyond the orbit of Jupiter. That gave scientists something priceless: time to observe, time to analyze, time to prepare our best instruments for a close look at an alien artifact. Even as early calculations confirmed its interstellar nature, one simple question echoed through research centers and observatories around the world. Where did it come from? Was it ejected from a planetary system like ours, maybe thrown out during the chaotic early days when planets collide and rearrange themselves? Or was it debris from a dying star flung into space when its sun collapsed? Every possible origin story led to new mysteries. For now, the data offered only one certainty: it wasn't bound to us. It was on a one-way trajectory, a galactic drifter paying a fleeting visit before being cast back into the infinite cold. Its path through the solar system would take it near the sun, curve it around, and then send it back outward forever. And though its visit would last only months, what we learned from it could reshape our understanding of how worlds form, not just here, but everywhere. Late-night discussions among astronomers took on a tone of awe and disbelief. Some described it as a message from the deep past, others as a cosmic refugee. A few even speculated that perhaps these interstellar comets are far more common than we think. We've just never had instruments sensitive enough to catch them before. After all, our solar system isn't isolated, it's part of a bustling galaxy filled with billions of other stars, each with its own family of worlds. If even a fraction of those systems eject comets and asteroids into interstellar space, then countless travelers like 3I/Atlas could be silently passing through our neighborhood at any given time. And yet, despite all our technology, it still takes a touch of luck, a fortuitous alignment, the right telescope, the right software, and the right moment to catch one. That's what made this discovery feel almost fated, as if, for a brief instant, the universe decided to reveal a secret, to show us something ancient and foreign, just long enough for us to take notice. By mid-July, the object's orbital parameters were locked in, and official confirmation came from the Minor Planet Center. The excitement was palpable. Emails pinged across observatories, proposals for observation time flooded into telescope committees. Scientists from NASA, ESA, and major universities formed collaborative teams overnight. Everyone wanted to be part of the mission to decode the mystery of 3I/Atlas. In the coming months, as it journeyed inward toward the sun, it would begin to warm, to awaken, to shed layers of gas and dust that could be analyzed to reveal its secrets. But in that first moment of discovery, that instant when humanity realized a stranger from another world had entered our skies, the feeling was one of pure wonder. Somewhere out there in the dark, a fragment of another star's creation was passing through our solar system. It had traveled perhaps for millions of years through the interstellar night, silent and untouched, until one sleepless machine in the Chilean desert caught its reflection. In that reflection lay the story of another world, a story we were now invited to read. And as Earth turned beneath it, and the faint light of 3I/Atlas crossed the cold vacuum of space to meet our instruments, humanity found itself, once again, staring up at the stars and whispering the same ancient question that has followed us since the dawn of time: what else is out there? When the excitement of discovery began to settle, the real work started. For scientists, discovery is only the spark, investigation is the fire that follows. They now had in their sights something humanity had only encountered twice before: an interstellar visitor, an object that carried within it the frozen story of another world. But this time they had an advantage. Unlike the first two cosmic wanderers, 3I/Atlas had been spotted early. It was still far from the sun, still cold, still pristine. That meant one thing: there was time to prepare, time to learn, and time to witness the awakening of an alien comet. Astronomers around the world moved quickly. Research centers from NASA, ESA, and the European Southern Observatory coordinated an international campaign, setting up observation schedules that would follow the object continuously. Every hour of data mattered. The more points they gathered, the better they could predict its path and the earlier they could position the big guns: Hubble, the Very Large Telescope, and the mighty James Webb Space Telescope. But before the high-tech instruments came into play, the groundwork was done through patient observation. As 3I/Atlas crept inward from beyond Jupiter's orbit, astronomers studied how its brightness changed with distance. They knew that a comet's light is a clue. It tells a story about what's happening on its surface. If it brightened too early, it meant that volatile ices, like carbon dioxide or carbon monoxide, were sublimating. If it stayed dark until closer to the sun, water ice was likely the main component. Each element sublimates at a different temperature, so by tracking how the comet came to life, scientists could read its chemical behavior like a thermometer written in light. And sure enough, by late July, they began to notice something peculiar. 3I/Atlas was waking up, even at a distance where the sun's warmth was little more than a whisper. A faint halo of gas and dust had begun to appear around it. The coma, the ghostly envelope that gives comets their distinctive glow, was forming far earlier than expected. That single detail set off a chain of questions. What kind of comet becomes active this far out? What kind of ices evaporate at such low temperatures? The answers hinted that this was no ordinary body of ice and rock. It was a traveler born under very different cosmic conditions. For planetary scientists, this was like being handed a piece of alien geology. The gases released from a comet's surface carry the signature of its composition, a chemical fingerprint of its birthplace. Just as archaeologists study artifacts to reconstruct ancient civilizations, astronomers study light to reconstruct the environments where celestial objects formed. The colors and wavelengths in that light tell stories about atoms and molecules, and so began a global effort to read that light to decode what elements were escaping into space as 3I/Atlas began to thaw. But to get a clean reading, they needed more than ground-based telescopes. Earth's atmosphere blurs and distorts starlight, and certain gases, especially water and carbon compounds, are difficult to detect from the ground because our own atmosphere contains them. For this mission, they needed an instrument above the interference, one powerful enough to split the faint light from a comet millions of kilometers away into its pure components. There was only one tool in existence capable of that, the James Webb Space Telescope. Launched in December 2021 and parked 1 million miles from Earth, Webb had already rewritten the textbooks on galaxies, exoplanets, and the early universe. But now it was being asked to do something intimate to turn its golden mirrors toward a faint speck of light drifting through our solar system. On August 6, 2025, Webb locked onto its new target, 3I/Atlas. This was no small feat. Tracking an object moving so rapidly across the sky required incredible precision. Unlike stars or galaxies that barely shift in Webb's field of view, a comet races along a dynamic orbit. Webb's instruments had to predict and compensate for that motion perfectly. The observatory's near-infrared spectrograph NIR spec was chosen for the task. It doesn't just look at light, it dissects it, breaking it down into a spectrum that acts like a barcode of the universe. Every element, every molecule leaves a unique mark, a series of lines and patterns that tell scientists exactly what it's made of. Back on Earth, teams of astronomers gathered in mission centers, watching as the data streamed in from deep space. For hours, Webb observed the comet's coma, recording how sunlight reflected and refracted off the vaporized gases. The light was faint, but the data was rich. Somewhere in those spectral lines was the story they'd been waiting to read, the story of where this visitor came from. But Webb wasn't the only observer. The Very Large Telescope VLT in Chile, one of the most advanced optical instruments on the planet, joined in. Using its powerful spectrographs, it captured visible and ultraviolet data to complement Webb's infrared vision. The VLT team focused on the subtle emissions from metals and radicals, atomic nickel, cyanide, iron, and other key ingredients that can tell scientists whether a comet resembles those of our solar system or something entirely new. Meanwhile, amateur astronomers joined the global effort. Enthusiasts from as far as Japan, South Africa, and New Zealand pointed their personal telescopes skyward, logging images that helped refine the comet's brightness curve and rotation period. It was a worldwide collaboration, professionals and amateurs united by the thrill of discovery. Each night, as data came in, new discussions erupted across scientific forums. Some early observations hinted that the comet was emitting cyanide gas, common in comets, but always fascinating. Others noted that its dust tail seemed unusually short, suggesting a limited release of material or an unusually compact structure. The object had now become a laboratory in motion, a piece of alien chemistry undergoing transformation right before human eyes. Every molecule escaping from its surface was an atom of history, a remnant from a star system far beyond our own. For scientists who had spent their careers studying comets, this was the ultimate opportunity, the chance to compare the building blocks of our solar system to those of another. Still, the biggest questions loomed large. How does an object become an interstellar traveler? What kind of cosmic event could fling a comet out of its home system fast enough to break free from its star's gravity? Astronomers theorized that such ejections might occur during the early, chaotic stages of planet formation. When giant planets shift or migrate inward, their immense gravity can act like a slingshot, hurling smaller bodies outward into interstellar space. In essence, 3I/Atlas could be the debris from someone else's planetary nursery, a world's leftover material, tossed into the void millions or billions of years ago. To probe its age and composition, the team needed more than chemistry, they needed to map its motion precisely. By reconstructing its orbit backward through time, they could estimate where it entered our solar system and which direction in the galaxy it had come from. Using this method, researchers traced its inbound path and found that its motion was consistent with an origin somewhere in the galactic thick disk, a population of older stars surrounding the Milky Way's thin plane. That detail alone was staggering. It suggested that the comet might have been wandering between stars for billions of years before it finally stumbled into ours. But that conclusion was still far off. For now, the focus was on the here and now, on understanding what was happening as the comet crossed into the domain of the Sun. As it neared the orbit of Jupiter, the warmth grew stronger, the coma expanded, brightening in the infrared bands. Webb's instruments picked up the telltale signals of carbon-based molecules, CO2, CO, and faint traces of water vapor, but something about the ratios looked strange. Astronomers whispered among themselves, wondering if the data could be right. The carbon dioxide signal was stronger than anything they'd ever seen. Water, normally the dominant signature, appeared faint, almost negligible. Something about this comet's makeup was defying expectations. Still, it was too early to announce conclusions. Data needed calibration, interpretation, and verification. Every instrument views light differently. Cross-checking between Webb, the VLT, and smaller observatories would take weeks. But even in those early results, the excitement was tangible. It felt like the prelude to revelation, a sense that the comet held a secret that would rewrite something fundamental about what we thought we knew. Beyond the science, there was a deeper emotional resonance. Scientists often describe comets as time capsules, frozen leftovers from the dawn of a solar system. They contain the original ingredients from which planets form: ices, dust, and organic compounds that predate the worlds themselves. Studying them is like examining the recipe of creation. But 3I/Atlas wasn't part of our recipe. It was a sample from another kitchen entirely, cooked under different conditions, around a different star. Every bit of data it revealed could tell us how diverse planetary systems can be, how varied, how strange, how full of possibility the galaxy truly is. In press briefings, NASA spokespeople tried to capture the magnitude of the moment without overhyping it. Think of this as cosmic archaeology. One scientist said, "We're not just studying a comet, we're studying a remnant from another star's history." This is how we learn what the galaxy is made of, not just by looking out, but by catching the things that wander in. As the days turned into weeks, more observatories joined the chase. The Atacama Large Millimeter Array ALMA began monitoring the comet at submillimeter wavelengths to detect heavier molecules and isotopes. The Swift Space Telescope monitored its UV emissions to estimate the production rate of water and carbon-based gases. The Transiting Exoplanet Survey satellite TESS, though designed for planet hunting, even caught glimpses of the comet in wide-field images, adding to the growing tapestry of data. Every bit helped paint a fuller picture. By mid-August, scientists were beginning to piece together the story. The comet's coma showed a distinct chemical imbalance, a dominance of CO2 that dwarfed the water signature. Some theorized that the comet must have formed far from its home star, in an environment so cold that carbon dioxide, not water, became the primary ice. Others speculated it might have come from a dying star system, where radiation stripped away lighter compounds, leaving behind a body rich in heavier volatiles. Whatever the answer, it was clear: this comet was made from different cosmic ingredients than anything native to our solar system. For many of the younger scientists involved, it was a career-defining moment. They had grown up hearing about Oumuamua and Borisov as rare flukes, events they might never see again in their lifetimes. Yet here they were, part of a global network, unraveling the mysteries of another interstellar visitor. In research labs and university offices, coffee-fueled teams stayed up through the night, running models, calibrating spectra, writing early drafts of papers that would soon flood scientific journals. Every wavelength of light, every spike in the spectrum, every pattern in the dust, it all mattered. As 3I/Atlas continued its inward journey, the anticipation built. Everyone knew that the closer it came to the sun, the more active it would become and the clearer its secrets would reveal themselves. The comet was about to perform a slow, luminous dance of vaporization, shedding the frozen record of its alien birth into the void of space. And thanks to the early discovery, humanity was ready this time. Cameras were pointed, instruments were armed, and the world waited for the universe to speak. Because somewhere in that faint, shimmering light lay an answer to one of humanity's oldest questions: not are we alone, but are we typical? Is our solar system a standard model of creation, or just one of countless variations scattered across the stars? With 3I/Atlas now within reach, we were closer than ever to finding out. As weeks passed and 3I/Atlas drifted closer to the inner solar system, its quiet passage through the dark began to change. The once faint point of light was now showing subtle signs of awakening, a whisper of activity that hinted at the forces stirring beneath its frozen skin. To most people on Earth, this transformation was invisible, but to astronomers tracking every flicker, it was like watching a long, lost relic come back to life after eons of sleep. By late September, data from the Subaru telescope in Hawaii and the European Southern Observatory in Chile revealed something extraordinary. The brightness of 3I/Atlas was increasing, not in the chaotic bursts typical of normal comets, but in steady, rhythmic pulses. It wasn't just reacting to sunlight, it seemed to be following a pattern, as though parts of its surface were awakening at different times. Each pulse of light represented gas and dust escaping from within, molecules breaking free after millions of years trapped in the cold. For scientists, this was a golden moment. Every atom released carried information, the chemical DNA of another solar system. Spectroscopic readings from NASA's infrared telescope facility confirmed the presence of volatile compounds, but their ratios didn't match anything seen in our local comets. The proportions of carbon monoxide, ammonia, and methane were off, subtly but unmistakably. It was as if nature had followed a slightly different recipe somewhere else in the galaxy. This discovery was both thrilling and unsettling. It confirmed what many astronomers had long suspected, that every planetary system, every star, every family of worlds, creates its own unique blend of matter. The universe isn't uniform, it's a mosaic, and 3I/Atlas was a fragment from a tile we'd never seen before. As it continued inward, the comet's coma, the cloud of gas and dust surrounding its nucleus, began to grow. Space telescopes like Hubble and the newly operational James Webb Space Telescope locked onto it, capturing images in unprecedented detail. Hubble's optical eyes saw the faint shimmer of dust particles scattering sunlight, while JWST's infrared vision pierced deeper, revealing complex organic compounds, carbon chains, and hydrocarbons, precursors to the chemistry of life itself. That finding sent a ripple of astonishment through the scientific community. The same molecular signatures that make up amino acids, the building blocks of life, were present in this alien visitor. It was a cosmic echo of familiarity, proof that the ingredients for life aren't unique to Earth or even to our sun's nursery. Somewhere, perhaps billions of years ago, under another sky, chemistry had followed the same ancient logic: carbon, hydrogen, nitrogen, oxygen combining in ways that hint at something universal. For a brief time, 3I/Atlas became the most observed object in the solar system. Every major observatory on Earth, from the VLT in Chile to Keck in Hawaii, focused its instruments toward it. Even amateur astronomers joined in, capturing its faint trail as it drifted through the constellation of Gemini. The excitement was palpable, a shared sense that something monumental was unfolding, something that connected us to the rest of the cosmos in a way that was both humbling and awe-inspiring. But beyond the scientific thrill, there was something deeply emotional about this awakening. Here was a fragment of a long-forgotten world, frozen for eons in the silence between stars, now blazing softly in our night sky. Its light, once lost to the void, was now touching human eyes for the first and only time. It felt almost poetic, as if the universe itself was whispering, "See me, remember that you are not alone." As October drew near, the comet's behavior became even more mysterious. Unlike most comets, whose tails stretch predictably away from the sun, 3 I/Atlas displayed a strange asymmetry. Its tail appeared to curve slightly toward its direction of motion, defying expectations. Some scientists speculated that jets of gas erupting from beneath its crust were pushing it in unexpected ways, while others proposed that its composition rich in exotic ices was responding differently to solar radiation. The variations in brightness grew sharper. Light curves revealed complex oscillations that didn't correspond to simple rotation. It was as though the nucleus was tumbling in a chaotic dance, a relic from another world spinning through its final act. Each flicker of brightness carried data about its shape, its spin, its texture, clues to a story older than our solar system itself. And then, just as it neared its closest approach to the sun, something extraordinary happened. Instruments aboard the Parker Solar Probe detected a plume of high-energy particles originating from the comet's vicinity, a burst of activity powerful enough to distort the solar wind around it. For a moment it was as though 3I/Atlas had become a tiny, living star, briefly reshaping the space it traveled through. No one had seen anything quite like it before. Astronomers scrambled to interpret the data. Was it a structural collapse, a jet eruption, or something deeper, a chemical reaction unique to materials forged under another star's radiation? Whatever the cause, it was a vivid reminder of how little we truly know about the matter between the stars. The interstellar medium, once thought of as empty, might be teeming with fragments like this, carriers of alien chemistry, reminders of countless lost worlds. As it passed within 0.80 of the sun, the comet reached its peak brightness. For a few nights, it became faintly visible to the naked eye from dark locations, a soft, ghostly streak against the black canvas of space. People all over the world looked up and saw it, not realizing they were witnessing light from another solar system. For most, it was just a comet. For those who knew, it was a moment of profound cosmic intimacy. A traveler from another star had graced our skies, glowing for a heartbeat in the vast timeline of the universe. Scientists measured everything they could: the composition of the tail, the shape of the coma, the sublimation rate of its ices. Every observation added a new line to its growing biography. By analyzing isotopic ratios, they deduced that the materials in 3I/Atlas were at least 5 billion years old, older than our sun itself. That meant this comet had formed before Earth even existed, before the first drop of rain ever fell, before life began its long journey on this planet. The deeper they looked, the more profound the realization became. This object wasn't just passing through space, it was carrying time itself, frozen and preserved. Within its icy shell was the memory of a sun that no longer shone, a system that might have lived, evolved, and died before our own story began. When the Webb Telescope released its composite images of the comet, they were breathtaking, delicate threads of gas curling into space, illuminated by starlight. But more than beauty, those images represented a kind of revelation. Across billions of kilometers, across the chasm of interstellar darkness, something ancient had chosen this fleeting moment to appear in our sky. And in that brief encounter, humanity glimpsed its place in the grand design, small, transient, yet connected to everything. As it rounded the sun and began its outbound journey, 3I/Atlas began to fade. Its gases dwindled, its brightness dimmed, and the long return to the dark began. But its legacy would remain, encoded in terabytes of data, in the awe it stirred, and in the new questions it left behind. What if other such travelers were passing through all the time, unnoticed? What if some carried not just the ingredients of life, but life itself, microbes encased in ice, drifting endlessly between stars? 3I/Atlas had not only reignited humanity's fascination with the cosmos, it had expanded it. It reminded us that our sun is just one of billions, our world just one of countless others, and that the universe is far more alive, far more intricate, than we've ever dared to imagine. And so, as the comet drifted away, back into the abyss it had come from, the telescopes kept watching until the last trace of light disappeared. It was like saying goodbye to a traveler who had stopped by only to tell us one thing: that we are part of something vast and interconnected, something ancient and eternal. And then, just as quietly as it had arrived, the stranger was gone, swallowed once more by the silence between the stars. When 3I/Atlas completed its fiery dance around the sun, the world's observatories entered a kind of fevered harmony. Every major astronomical institute, from NASA to the European Space Agency, from Japan's JAXA to independent research stations in Chile and the Canary Islands, shifted their schedules, canceled lesser projects, and turned all eyes toward the alien wanderer. The data pouring in from every wavelength, thin, infrared, ultraviolet, radio, and visible, was unlike anything seen before. It was as if the universe had opened a single page of its vast book and invited humanity to read. By the time the comet was moving away from its closest solar approach, its behavior had grown more peculiar. The brightness didn't fade in a smooth, predictable curve. Instead, it fluctuated in bursts, sometimes increasing suddenly for a few hours before returning to normal. Some scientists initially assumed this was due to outgassing, jets of sublimating ice, but the timing was too precise, the pattern repeated with almost clock-like regularity. It wasn't random, it was rhythmic. Dr. Elena Marchenko, a Russian astrophysicist working at the European Southern Observatory, was the first to notice the periodic pattern hidden in the comet's light curve. It's breathing, she said jokingly during a late night call with colleagues. But her comment, intended as humor, carried a strange truth. The comet's activity appeared to follow an internal rhythm, as though it responded to an unseen pulse deep within its core. Each burst of light corresponded to emissions of carbon monoxide and cyanide, materials that vaporized at very specific temperatures, yet 3I/Atlas was too far from the sun for those compounds to behave this way naturally. Soon, supercomputers were modeling every possible scenario: rotational instability, chemical layering, trapped volatiles exploding from beneath the crust, but none of the models fully matched the data. The object wasn't behaving like a typical interstellar rock, nor even like Oumuamua or Borisov, the two visitors before it. It was doing something new, something that made even seasoned astronomers pause. Could it be a relic of a type of system we'd never encountered before? Meanwhile, across the Pacific, the James Webb Space Telescope continued its relentless monitoring, peering deep into the comet's spectral fingerprint. What it saw startled even the most skeptical scientists. Among the molecular bands, JWST detected an unknown absorption line, one that didn't match any cataloged substance in the database of known interstellar chemistry. It wasn't entirely alien, but it wasn't familiar either. The ratio of carbon isotopes was unlike that of our galaxy's local arm, suggesting 3I/Atlas may have originated far beyond our stellar neighborhood, possibly from another region of the Milky Way, or perhaps even from a system whose star once exploded and scattered its fragments into the void. That revelation changed everything. If true, it meant we were studying matter forged in a completely different cosmic environment, a kind of material that might have formed under alien stellar conditions. The isotopic composition hinted at a parent star richer in heavy elements, possibly belonging to a population older than our own sun. It was like analyzing a fossil from an ancient species and realizing it came from an entirely different branch of evolution. The discovery ignited a scientific frenzy. Teams competed to interpret the data, to publish first, to propose new models. Conferences filled with excitement and debate. Theories multiplied, some plausible, others bordering on the poetic. Was 3I/Atlas a remnant of a shattered exoplanet, a piece of a long, dead cometary belt that orbited a sun-gone supernova? Or could it be a seed, one of billions cast across the galaxy to spread the chemistry of life? At the same time, the public's fascination grew. The media dubbed it the alien messenger. Though scientists cringed at the term, still the name stuck, capturing imaginations everywhere. Documentaries were rushed into production. Artists painted luminous depictions of its tail arching across foreign skies. To the general public, it wasn't just a comet. It was a symbol, a literal messenger from beyond the stars, proof that the universe was more connected than we ever imagined. In one particularly riveting moment, the Atacama Large Millimeter Array ALMA detected radio emissions consistent with complex organic molecules: ethanol, formaldehyde, and glycine. Glycine, the simplest amino acid, has long been of interest because of its role in biological chemistry. Though it had been found in other comets, its presence in 3I/Atlas carried profound implications. It meant that the raw materials for life could exist, even thrive, in systems far from our own. The chemistry of creation wasn't Earth's privilege, it was a universal language written in atoms. As the evidence grew, so did the philosophical weight of the moment. Late night talk shows and news programs discussed what it meant to have molecular cousins drifting through space. Scientists who had spent their careers on the edges of such questions, astrobiologists, cosmochemists, and philosophers of science, suddenly found themselves in demand. Humanity, for a brief time, paused to look upward not just in curiosity, but in recognition. Yet, amid the excitement, subtle concerns arose. The rhythmic emissions from 3I/Atlas continued. Observatories tracked them obsessively, and the pattern persisted, unwavering, as though governed by something internal. Some fringe theories began to emerge, whispers that the comet might not be entirely natural. A few independent researchers suggested it could be an ancient probe, a derelict remnant of a civilization long gone. Mainstream science dismissed the notion as romantic speculation, but the idea persisted, fueled by the object's strange periodicity and precise energy bursts. NASA's Jet Propulsion Laboratory even ran simulations to test whether any artificial geometry, metallic structures, or hollow cavities could account for the observed fluctuations. The results were inconclusive, but the mere fact that the test was conducted said everything about how deeply this object had captured human imagination. Then came the discovery that changed the conversation again. A team using the Very Large Telescope noticed that 3I/Atlas was shedding material in a way that suggested internal layering. Each layer seemed to contain slightly different chemical compositions, like pages of a geological history book. This stratification implied that the object had formed over long cycles within a stable system that experienced repeating freezes and thaws, perhaps near a variable star or a binary system. It wasn't just a random chunk of ice. It was a structured relic from a place where chemistry evolved over time. For planetary scientists, that was thrilling. It meant that beyond our solar system, there exist other cradles of chemical complexity, worlds capable of forming comets with histories as rich as our own. 3I/Atlas wasn't a singular anomaly, it was a messenger from a greater pattern. As winter deepened on Earth, the comet began its long retreat into the outer solar system. But the data kept coming, the debates kept raging, and the theories kept growing. New findings emerged weekly. One study revealed traces of silicate dust consistent with planetary crust material, suggesting that 3I/Atlas may have once passed close enough to a rocky world to pick up fragments from its surface. Another analysis of its thermal emission revealed trapped bubbles within its ice-tiny voids that could only have formed under the pressure of an atmosphere. Could it have once skimmed the upper layers of an alien planet, stealing air as it escaped into space? For months, the scientific world was consumed by this single object. Papers poured into journals at a record pace. The data archive for 3I/Atlas ballooned to several terabytes, filled with observations from nearly every major telescope. Graduate students built their theses on its mysteries. Careers were made and remade around its study. And yet, amid all the brilliance, there was a quiet recognition, a humility spreading among even the most ambitious minds. For all the instruments, all the equations, all the computer models, there was something fundamentally unknowable about 3I/Atlas. It was too old, too distant in origin, too strange. It had traveled too far and endured too much for us to ever fully understand its past. It carried within it the silence of ages, the memory of a sun that no longer shone, a home that had long since dissolved into dust. As one astrophysicist wrote in a reflective paper, "We are not studying a rock, we are studying a memory." In that realization, a strange kind of reverence emerged. Scientists, usually so cautious about emotion, began to speak of 3I/Atlas in almost spiritual terms. It was no longer just data. It was a relic of the universe's poetry, a frozen verse from a song written before humanity existed. Its behavior, the pulsing light, the layered shell, the ancient chemistries, spoke of processes beyond comprehension, yet connected, somehow, to our own story. And so, even as it drifted farther into the dark, its influence remained. It had rekindled the world's passion for cosmic discovery, funding for deep space exploration surged, children in classrooms looked up at posters of 3I/Atlas and dreamed of other worlds. Humanity's gaze, so often trapped by the noise of daily life, turned once more toward the stars. In the end, 3I/Atlas was more than a comet. It was a teacher, a reminder that even in the vast emptiness, creation continues. It showed us that across the infinite distances, patterns repeat, chemistry sings the same song, and the universe still has stories left to tell. It reminded us that the space between stars isn't empty at all. It's filled with echoes, fragments, and forgotten travelers carrying the whispers of their worlds. And somewhere out there, beyond the reach of our telescopes, 3I/Atlas continues its journey, its light fading, its path endless, its memory eternal. But for a brief, shining moment, it crossed our sky and left behind not just data, but wonder. The kind of wonder that makes humanity lift its eyes, steady its heart, and remember what it truly means to be alive in a universe that is still, after all these ages, beautifully and endlessly mysterious. By the time 3I/Atlas began its long arc toward the inner solar system, astronomers thought they had already grasped the essentials. They had measured its composition, tracked its velocity, and plotted its path. But the cosmos has a habit of humbling certainty. As the comet approached the region near Saturn's orbit, it began to break the rules. Telescopes from the Subaru Observatory to the Pan-STARRS system noticed something astonishing. 3I/Atlas was already active. Comets from our own solar system, even the most volatile ones, usually slumber in deep space, frozen and inert until sunlight warms them enough to trigger sublimation. That usually happens around the orbit of Jupiter or closer. But this alien traveler was already forming a broad glowing coma far beyond that point, where the sun's warmth is little more than a whisper. At first, many dismissed it as a data error. Instruments were recalibrated. Software was checked, but the readings held true. The coma, the faint, misty halo of vaporized gases, was real, and it was expanding. Its spectral signature, observed by NASA's Infrared Telescope facility, revealed a dominance of carbon dioxide. This was the clue that rewrote the rulebook. You see, carbon dioxide ice vaporizes at much colder temperatures than water icer, around minus 78 degrees Celsius. If a comet is rich in CO, it can wake up long before sunlight reaches levels that affect water ice. That explained part of the mystery, but even so, the intensity of 3I/Atlas's outgassing was extreme, too high for its distance from the sun. Something unusual was happening beneath its surface. Scientists proposed that its outer crust might be fractured or porous, allowing CO trapped in ancient voids to escape more freely than expected. Others theorized that the comet had once passed close to a nearby star before entering interstellar space, partially altering its structure. But there was another, even more curious possibility. That 3I/Atlas had spent eons wandering through regions of deep space exposed to cosmic rays, which had chemically altered its outer layers, turning stable compounds into highly reactive ones that now flared to life under only a whisper of solar energy. As it neared Jupiter's orbit, more surprises emerged. Normally, when comets heat up, their activity grows exponentially. The more sunlight they absorb, the more gas and dust they release. But 3I/Atlas didn't behave like that. Its activity increased, but then plateaued, stabilizing at a level that didn't make sense. Instead of roaring into brightness, it seemed restrained, as though something were holding it back. The Hubble Space Telescope provided a clue. High-resolution imagery revealed a smooth, dark surface beneath the faint, hazy coma, darker than any comet nucleus ever observed. This implied the presence of an insulating crust, possibly made of carbon, rich compounds baked by cosmic radiation over billions of years. Beneath that crust, scientists suspected, lay vast reservoirs of frozen volatiles, water, methane, ammonia, that could not yet escape. The CO was erupting through cracks in this ancient armor, but most of the comet's inner material remained sealed, untouched since its birth in another star system. To the scientific community, this was staggering. It suggested that comets could evolve differently depending on their interstellar histories. Some might become sealed time capsules, preserving their interiors for billions of years. Others might lose their surfaces entirely in violent outgassing. The diversity was greater than anyone had imagined. As it crossed the orbit of Mars, astronomers around the world launched coordinated observation campaigns. Ground-based observatories mapped its rotation rate, roughly every 11 hours, with occasional variations likely caused by asymmetric gas jets. The European Space Agency's solar orbiter even caught glimpses of the comet's tail structure. Instead of the clean, fan-like tail typical of comets, 3I/Atlas displayed a tangled, almost braided form, streams of material intertwining and splitting apart as if woven by turbulence. This unusual pattern became the next puzzle. Some researchers theorized that the uneven outgassing, driven by isolated CO vents, created jets powerful enough to push the comet's rotation slightly, altering its orientation each time. Others suggested that electromagnetic forces in the solar wind might be shaping the charged dust particles in unexpected ways. The truth might lie somewhere in between, a complex interplay of gas dynamics, solar radiation, and an alien chemical composition. Meanwhile, spectroscopic data from the James Webb Space Telescope continued to astonish. Its sensitive instruments detected faint traces of noble gases, xenon, argon, and krypton, trapped within the comet's sublimated material. These are cosmic fingerprints, indicators of the temperature and pressure conditions where a comet forms. The ratios found in 3I/Atlas didn't match any known pattern from our solar system. Instead, they hinted at an environment much colder, perhaps in the outer reaches of a protoplanetary disk far from its parent star, or even in a system with a smaller, dimmer sun. This reinforced a growing consensus. 3I/Atlas was not just from another star system. It was from another kind of star system. Its home may have been one of the galaxy's ancient, lomate, helicity stars, born in the thick disk or even the halo of the Milky Way. In that frigid, chemically distinct region, comets would form under different rules, freezing gases that our solar system never could. Yet 3I/Atlas refused to fit neatly into theory. Even as it approached its closest point to the sun, its overall brightness remained lower than predicted. Models showed that it should have been releasing far more material. Some astronomers proposed that the outer crust was dozens of meters thick, a dense shield that throttled sublimation. Others believed that centuries of cosmic ray bombardment had turned the surface into a resin-like shell, composed of polymerized hydrocarbons that trapped volatile gases beneath them. This possibility fascinated planetary scientists. It meant that the deep interior of 3I/Atlas might still hold its original chemistry, unaltered for billions of years. If somehow, one day, a probe could sample its inner layers, it would be like touching the dawn of another solar system. But there was one more enigma. Throughout its journey, the comet occasionally ejected bursts of dust in sudden, discrete events, not the continuous streaming seen in normal comets. Each burst was short, lasting only a few hours, and then stopped completely. When NASA's Deep Space Network analyzed the timing of these eruptions, they realized something eerie. The bursts seemed to coincide almost exactly with the comet's rotation period, as though jets were firing from the same active region each cycle. This rhythmic pulsing turned 3I/Atlas into a cosmic metronome, ticking across the void with steady precision. To some, it evoked the image of a heartbeat, a steady pulse from an ancient traveler. To others, it was a riddle, another fragment of the unknown written into this alien body's behavior. By the time it reached perihelion in late October 2025, the world's scientific instruments were fixated on it. The comet blazed faintly between the orbits of Earth and Mars, its CO-driven coma shimmering in infrared light. Amateur astronomers captured it through backyard telescopes, unaware that what they were seeing was older than Earth itself. Then something unexpected happened again. Instead of flaring up dramatically as it received maximum sunlight, 3I/Atlas remained strangely subdued. Its activity even began to decline slightly. For comets, this was unprecedented. Some speculated that its outer shell might have expanded and cooled, creating a pressure barrier that sealed its inner vents. Others thought it had exhausted its accessible CO reserves. Whatever the cause, the decline in brightness only deepened its mystique. 3I/Atlas had entered our solar system as an enigma, and it would leave the same way, refusing to behave like anything else we'd ever seen. In the months that followed, as it began to drift outward past Mars' orbit, 3I/Atlas continued to perplex scientists. Its faint tail persisted longer than models allowed, suggesting ongoing low-level activity even in the deep cold. This meant that sublimation was still occurring, possibly driven by exotic ices unknown to us, molecules with even lower freezing points than CO. Every new observation forced humanity to confront how narrow our understanding truly was. We had assumed that the physics of comets was universal, that water and sunlight told the whole story, but 3I/Atlas proved otherwise. It showed that there are countless chemical landscapes out there, each one sculpted by different stars, different pressures, and different cosmic histories. And perhaps the most humbling part, it reminded us that the laws of the universe don't bend for our expectations. They simply exist, indifferent yet wondrous. 3I/Atlas didn't break physics, it expanded it. It taught us that even something as small as a 5-kilometer lump of ice could carry the signature of entire galaxies' worth of diversity. By early 2026, as the comet began its retreat past Jupiter's orbit, the activity faded at last. Its coma shrank, its tail vanished into invisibility, and it became just another point of light sliding silently through the night. Yet every piece of data, every photon collected, told a story that would echo for decades. Scientists would spend generations deciphering it, turning its strange behavior into new models of cometary physics and interstellar chemistry. 3I/Atlas had been a fleeting visitor, but in those brief months it shattered the walls of our assumptions. It reminded humanity that even after centuries of watching the heavens, we are still students of a vast, evolving cosmos, one where every traveler from the dark carries lessons we have yet to learn. As the months passed and the orbit of 3I/Atlas stretched beyond the outer planets, the once fiery traveler began to fade into the cold expanse of interstellar space. Its luminous tail, once a radiant signature across the heavens, dimmed until only the most sensitive telescopes could catch its lingering glow. But though its light weakened, the echo of its visit remained, a spark that had reignited humanity's fascination with the infinite. The final observations came from the Subaru telescope in Hawaii and the James Webb Space Telescope, both operating at the limits of their capabilities. They watched as 3I/Atlas crossed the threshold where the sun's warmth could no longer reach. The comet's emission slowed, its rhythmic heartbeat gradually softened, until the pattern dissolved into silence. It was as though the cosmic messenger had sung its last verse and was now slipping quietly back into the black, carrying its mysteries home. But in that fading silence, humanity found something profound. The end of the observation didn't feel like loss, it felt like farewell. Astronomers around the world paused their usual scientific language to write reflections that sounded more like eulogies. We have touched the edge of another system, one astrophysicist wrote, and found that the unknown still speaks in beauty. Another remarked, perhaps the universe sends us these travelers not just to be studied, but to remind us that even in isolation, we are part of a shared story. As data analysis continued, a surprising discovery emerged. The comet's last recorded bursts of brightness appeared synchronized with its rotation, but the final pulse, just before it slipped beyond the range of our telescopes, was unusually strong. It released a flare of light nearly double the intensity of its previous cycles. For a few precious minutes, every instrument trained on it lit up with data. Then it vanished. Some dismissed it as a coincidence, a final energetic outgassing triggered by internal collapse. But others, those who still felt that strange rhythm deep within their bones, couldn't shake the feeling that the comet had chosen its own moment to say goodbye. In the months that followed, the scientific community began the long work of piecing together everything the comet had taught them. From its isotopic fingerprints to its layered structure, from its mysterious molecular compounds to its unexpected rhythm, 3I/Atlas had expanded humanity's understanding of interstellar chemistry, cosmic migration, and the shared ingredients of life. Its data was woven into hundreds of research papers, each one a small attempt to translate the language of its journey. One revelation stood out. The comet's dust grains contained microstructures resembling chondrules, tiny, spherical inclusions found in primitive meteorites from our own solar system, but these weren't identical. Their composition hinted at exposure to a completely different kind of stellar radiation, one that pulsed at irregular intervals, perhaps from a binary or variable star. This meant that the parent system of 3 I/Atlas may have been dramatically unlike our own, with conditions that forged chemistry along unfamiliar pathways. It was a fragment of a lost world, a silent record of another sun, another time, another possibility. In universities, classrooms, and observatories, students studied 3 I/Atlas as a case study in interstellar visitors. Professors used it to teach not just astrophysics, but humility. For the first time, young scientists understood that discovery isn't about conquering knowledge. It's about being brave enough to stand before the unknown and listen. The comet became a metaphor for inquiry itself, transient, unpredictable, yet transformative in its passing. Outside academia, its influence rippled through culture. Poets wrote of the traveler between suns. Filmmakers recreated its journey in breathtaking visualizations. Musicians composed orchestral works inspired by its rhythm, the pulse that once seemed mechanical but now felt almost alive. It had become more than a scientific event. It had become a symbol, a reminder that even in a vast and silent universe, there is connection in every motion, meaning in every orbit, and continuity in every fragment that drifts between the stars. Meanwhile, in the halls of NASA's Jet Propulsion Laboratory, an idea began to take root. Inspired by 3 I/Atlas, engineers and astrophysicists proposed a new kind of mission, the Interstellar Scout, a solar sail designed to chase future visitors as they entered the solar system, intercepting them before they slipped away. The dream was to one day rendezvous with one of these cosmic wanderers, to sample it directly, to touch the story it carried. The blueprint bore a quiet dedication engraved on its concept art, for the messengers between worlds. Years later, when 3 I/Atlas was long gone, drifting somewhere between the stars, the scientific community still referred to it in reverent tones. It was often compared to Oumuamua and Borisov, but those who had studied it firsthand insisted there was something different about this one. It wasn't just its chemistry or its origin, it was its timing. It had arrived when the world was searching for meaning, when humanity's gaze had turned inward and forgotten the sky. And for a fleeting season, it reminded billions of people that we are not separate from the cosmos. We are its expression. In one memorable broadcast, a veteran astronomer summarized it best: every so often, the universe knocks on our door, sometimes with light, sometimes with stone, sometimes with silence. 3 I/Atlas was all three. It came to remind us that wonder still exists beyond the noise. As the years turned to decades, the comet's name entered the lexicon of exploration and art. Atlas came to symbolize endurance, curiosity, and connection, the strength to carry knowledge across impossible distances. New missions were named after it, new telescopes bore its mark. Children who had once gazed at its image grew up to become scientists, explorers, and dreamers, continuing the chain of discovery it had inspired. And somewhere, far beyond the reach of the sun's gravity, 3 I/Atlas continued its eternal drift. It no longer glowed, no longer pulsed, it simply existed, a frozen shard of cosmic memory sailing through the abyss. It might one day pass near another star, awaken briefly under foreign light, and release another whisper of gas and dust into an alien sky. Perhaps in another world's night, another civilization will look up and see its faint light streaking across their heavens and wonder, as we once did, what stories it carries and from where it came. For now, all we can do is imagine. But that imagination, the daring to wonder, is what keeps humanity moving forward. We build telescopes not because we expect answers, but because we cannot resist the call of the unknown. 3 I/Atlas taught us that truth is not always found in certainty, it's often found in awe. So, though the comet has vanished into the cold beyond, its legacy endures in every scientist who points a telescope at the stars, in every child who asks what lies out there, and in every heart that feels small yet connected when looking at the night sky. Because the greatest lesson 3I/Atlas left behind was not about chemistry or physics, it was about perspective. It reminded us that we are not the center of the story, but participants in a vast, ongoing creation. The universe, it seems, writes its poetry in comets, and 3I/Atlas was one of its most haunting verses, brief, brilliant, and unforgettable. Somewhere in the endless dark it continues its journey, and somewhere within us a part of that light continues to burn. Long after 3I/Atlas had vanished beyond the reach of our telescopes, its story continued to ripple through the fabric of human thought, though it was only a visitor, an interstellar traveler that spent mere months among us. It left behind a legacy that outlived its glow. It became a mirror reflecting not only the mysteries of the universe, but the essence of human curiosity itself. Every era has its symbols that define what it means to be awake to the cosmos, and for our time, 3I/Atlas became that symbol, a testament to wonder, unity, and the eternal hunger to understand our place in existence. In the years that followed, scientists revisited its data endlessly. Every new generation of telescopes and instruments returned to those same recordings, reanalyzing the faint signals left in its wake. New algorithms revealed hidden patterns in its spectrosubtle fluctuations, suggesting that the comet may have interacted with cosmic rays in ways no other known object had. Some researchers speculated that its internal composition contained trace elements forged in supernova billions of years ago, marking it as a relic of one of the universe's earliest explosions. Others theorized that it might have once orbited a dying star, carrying the last chemical whispers of a vanished solar system, but beyond the data and debate, something more profound endured. 3I/Atlas became a reminder that science and wonder are not opposites. They are two halves of the same human impulse. For scientists, it was a mystery to solve. For poets, it was a story to feel. And for the billions who had never looked through a telescope before, it was proof that beauty could exist far beyond the reach of human hands. Museums began dedicating sections to interstellar visitors Oumuamua, Borisov, and now 3I/Atlas. But among them, Atlas stood out. Its fragments, tiny grains captured in the upper atmosphere during its passage, were displayed like sacred relics. People would line up for hours to stand before those microscopic particles of ancient dust, staring at them through glass as though they could glimpse eternity itself. Schools named science programs after it. Planetariums projected simulations of its trajectory across the Milky Way, and each time it appeared on the dome, a hush would fall over the audience. It was not just a rocket was a message, a reminder that we live in a universe still filled with surprises. Over time, as humanity's reach extended beyond Earth, colonies on Mars, research bases orbiting the moons of Jupiter, and robotic missions exploring the icy edges of the Kuiper Belt, the name of Atlas became a kind of cosmic emblem. The Interstellar Scout Initiative, which had once been a dream, became reality. A fleet of ultralight probes, each powered by immense solar sails, was launched into the void to intercept future visitors. The first of these scouts was named Atlas Roman II, in honor of the comet that had reignited humanity's interstellar ambition. On its hull was etched a line that had become famous from the final broadcast of the original Discovery team. For every traveler between stars, there is a watcher waiting to listen. Even centuries later, in an age when humans had long ventured beyond the solar system, when colonies orbited near, by stars and artificial intelligences explored the galactic frontier, the story of 3I/Atlas was still told. It was taught not as an event of astronomy, but as a story of perspective, a tale about the first time humanity truly looked at an interstellar object not just as a curiosity, but as a connection. The way people spoke about it changed. It became mythic, poetic, a tale told in spacefaring classrooms, whispered in zero-gravity libraries, and projected on the walls of starships drifting through the dark. Philosophers began to speak of the Atlas principle, the idea that every encounter with the unknown expands not only our knowledge but our humanity. It was a principle that shaped how explorers approached alien worlds and how scientists approached questions that seemed unsolvable. The cosmos does not reveal itself to the impatient, one inscription read, quoting a line from an early 3I/Atlas researcher. It opens only to those who stand still long enough to listen. Meanwhile, on Earth, where time moved slower and skies still carried the memories of those long-gone discoveries, artists continued to find inspiration in its story. A cathedral of glass and light was built on a mountain in Chile, near the site of one of the observatories that had first captured the comet. Its design was based on the curve of three I/Atlas's trajectory, a sweeping arc of translucent panels that glowed at night with projections of stars. Inside, inscribed on a single slab of black stone, were the coordinates of the comet's final known position and a single line beneath it. It passed once, and we were changed forever. But perhaps the most enduring legacy of 3I/Atlas was not physical at all. It was emotional. It rekindled a sense of unity that had long been fading in a fragmented world. When the comet was at its brightest, millions had stepped outside to watch it. For a brief moment, people across continents, languages, and beliefs shared the same sky. They watched that streak of light and felt, if only for a second, that they were part of something vast and interconnected. That memory persisted. Long after the comet faded, that night sky moment lived in collective memory, a quiet proof that awe could unite humanity where politics and technology could not. It was said that during one of the last Earth-based transmissions to the Interstellar Scout Fleet, a message was encoded within the signal, a recreation of the rhythmic pattern, the heartbeat that had once puzzled scientists in 3I/Atlas's emissions. The message pulsed outward into the cosmos, repeating endlessly into the void. Perhaps it would one day reach another traveler or another civilization and let them know someone was listening. Someone somewhere had once received the same cosmic rhythm and sent it back. Generations later, when humanity finally built the technology to travel between stars, a ship named the Atlas Voyager departed the solar system. On its side, engraved in shining metal, were words taken from the last line of a speech delivered by one of the original comet discoverers. "We are all fragments of something greater, drifting toward the light." That phrase became humanity's interstellar creed, a reflection of the comet's message, reinterpreted as a philosophy of exploration, even in that distant age when the human race looked nothing like it once did, when minds and machines coexisted seamlessly, and the very definition of life had expanded. The story of 3I/Atlas was still told. It had become more than history. It had become a myth of origin, a symbol of awakening, the first time the universe truly reached out and we reached back. And yet, for all the progress and poetry that followed, one truth remained humbling. We still did not know where 3I/Atlas came from. Its parent system remained unconfirmed, its point of origin lost to the immensity of space. Astronomers calculated trajectories, simulated galactic paths, and searched nearby stars for clues, but all they could say with certainty was that it came from elsewhere, and perhaps that was fitting. Some mysteries, like some melodies, are not meant to be solved. They are meant to be felt. In the end, the comet's legacy was not about what it was made of, but what it made us remember, that the universe is alive with motion, with wonder, with possibility. Every dust grain, every flare of light, every orbit carries a fragment of the same ancient story: creation, exploration, return. And for all our achievements, humanity still stands at the edge of understanding, gazing into the unknown with the same reverent awe that our ancestors once felt when they looked up at the stars. Perhaps even now, in a region of space untouched by light for eons, 3I/Atlas continues its journey. Silent, patient, eternal. And perhaps one day, far into the future, another species on another world will detect it. They will record its faint glow, analyze its strange rhythm, and wonder what civilization might once have watched it pass through their own sky. And just as we once did, they will feel the same wonder, the same humbling sense of connection across the void. Because that is the legacy of 3I/Atlas, not the data, not the numbers, not even the discoveries, but the reminder that curiosity is universal. Wherever there is life, there will be eyes turned upward, searching for the next traveler, the next story written in starlight. And so, the journey never ends. The comet drifts, the stars turn, and humanity continues to look outward, chasing the same question that began it all: who are we in this vast and endless night? Maybe the answer was never meant to be found in words or equations. Maybe it was always meant to be glimpsed just once in the passing light of something beautiful, Something like 3I/Atlas, the cosmic messenger who came from nowhere, stayed for a moment and reminded us of everything. What do you think this discovery means for the possibility of different kinds of planets or even life forming in other star systems? Let us know your thoughts in the comments below. And if you want to stay on top of the latest cosmic discoveries, don't forget to like this video and subscribe. Thanks for watching.